In this video, we're going to review equivalent definitions of linear independence. We're also going to look at examples of using these definitions to decide whether or not a set of vectors is linearly independent. And then just for later, when you're looking back at these after we've done a bit more material, we're going to use the determinant to decide whether or not a set of n vectors in Rn is linearly independent. When you're first watching through these, you can skip that final step. So I think the most intuitive definition is definition 0. We say that a set is a linearly independent set if no vector is a linear combination of the others in the set. If you want to think about this in terms of directions that you can go by taking different linear combinations of vectors, each vector will provide a new or unique direction. So leaving any one of these vectors out of our set will mean that we can explore a smaller space. Okay. So an example of this is if we have the set 1, 0, 0, 0, 1, 0, 0, 0, 1. This is a linearly independent set. Each of these vectors gives us a different direction in R3. And if we were to omit any one of these vectors, the set of points that we can explore shrinks. In contrast, the second set 1, 0, 0, 0, 1, 0, 2, negative pi 0 is a linearly dependent set, or another way of saying this is that it's not linearly independent. And that's because this third vector here can be written as a linear combination of the first two. And what that means is that this direction is nothing new. We could have gotten it from the other two directions. So we could safely omit this vector without changing the set of points that we can explore. Definition 1 says that a set is linearly independent if for every vector in their span, there's only going to be one way to write V as a linear combination of the vectors. So there's only one set of scalars, C1, C2 through Cn, that will give us the vector V. A sort of silly example of this is that if we take the vector V1, this is equal to just 1 times V1 plus 0 times V2 plus 0 times Vn. The only way, this is the only way to get V1 as a linear combination of elements in this set. Okay. So we started really specifically looking at whether or not elements of this set can be written in terms of other elements of the set. Then we expanded this to say anything that's a linear combination is only a linear combination in one single way. Now when we want to get something that we can check easily, we're going to go to definition 2, which says that in particular, if we can show that there's only one way to write the vector 0 as a linear combination of V1 through Vn, then our set is going to be linearly independent. So we can always write the vector 0 just as 0 times V1 plus 0 times V2 plus 0 times Vn, as long as there are no other ways of writing it as a linear combination, our set is going to be linearly independent. Okay. So one standard way of checking for or against linear independence is using definition 2. So definition 2 says that a set is linearly independent if the vector 0 has only one way of being written as a linear combination of V1 through Vn, and that is just by multiplying each one of these vectors by the scalar 0. Notice, though, that we can rephrase this problem in terms of a matrix vector product. So on the right-hand side, we can write this as a matrix, V1 through Vn, where we know all of these columns, times an unknown vector, C1 through Cn. Now we know one solution, which is multiplying the zero vector. The zero vector multiplied by any matrix is going to give us a zero vector. And we're going to be linearly independent if this is the only solution to this matrix vector equation. Okay, so our general steps are that we're going to form the matrix whose columns are given by the vectors in our set. We're going to row reduce, and we're going to say that our set is linearly independent if solutions to AV equals 0 are unique. So there's going to be a pivot in every single column. In other words, there are going to be no free variables. So let's try this out with an example. Here we have 3 vectors, and we want to know whether or not they form a linearly independent set. So we're going to form the matrix, which has these 3 vectors as its columns, and then we're going to row reduce it. So row 2 is going to be row 2 minus row 1. Row 3 is going to be row 3 minus row 1. And we can keep going. Row 3 is going to be row 3 minus 3 row 2. And at this point we can see that we're going to have a pivot in every column. So no free variables. And the result is that that means that all solutions are unique. There's only ever one solution. So unique solutions means that our set is linearly independent. So we're going to try out another example. We want to decide whether or not these 3 vectors form a linearly independent set. And so our first approach is to use definition 2. We're going to build a matrix whose columns correspond to these vectors and row reduce it and see whether or not we have unique solutions. So let's do the row reduction. Okay, so we produce this matrix by clearing out all of the values below our first pivot. And now if we replace row 3 with row 3 minus row 2, we see that we are going to have a column that lacks a pivot. Okay, so there's a pivot in column 1, in column 2, but not one in column 3. We see there are not enough pivots, so there's a free variable. Our final variable is free. And what that means is that we're going to have non-unique solutions. So this means that our set is linearly dependent. In some cases, like in this example, it can also be helpful to go back to some of the earlier definitions. For example, definition 0, which says that a set is linearly independent if no vector in the set is a linear combination of the others. So sometimes we get lucky and we can see linear combinations pretty easily. if we stare at this for a moment, we can see that V3, which is 4, 6, 10, can be written as V1 plus V2. And from this we can conclude that our set is linearly dependent. That is, it's not linearly independent. If you happen to notice one of these conditions, a linear dependence in this way, it can be faster than going through and doing a row reduction of a matrix. A standard way for checking for or against linear independence, which is a little bit more advanced, is as follows. If we've got n vectors in Rn, we can form a square matrix A, which is just, as before, each column is one of the vectors in our set. And we're going to find the determinant. Our set is going to be linearly independent if and only if the determinant of our matrix is non-zero. Let's take a look at an example now to see how this works. So we have the following three vectors. We want to decide whether or not they form a linearly independent set. So I'm going to build a matrix that has as columns these vectors. I'm going to call this matrix A, and then calculate the determinant of A. Okay, I'm going to do this by a cofactor expansion. Let's do it in the top row. Okay, so we have 1 times the determinant of 3, 2, 5, 3, minus 2 times the determinant of 1, 2, 1, 3, plus 1 times the determinant of 1, 3, 1, 5. So we get 1 times 9 minus 10, minus 2 times 3 minus 2, plus 1 times 5 minus 3. Or negative 1 minus 2 plus 2. Our determinant is negative 1, which is not equal to 0. So our vectors, our set is linearly independent. All right, this has the advantage that sometimes we'll be calculating the determinant anyway. So knowing the determinant will be enough to tell us whether or not our vectors are linearly independent.